Welcome to module 20 of database management systems. We have been discussing about relational database design since the last 4 modules, and this will be the concluding part of relational database design. In the last module, we have seen some very key concepts of relational design, that of normal forms, third and Boyce code normal forms specifically, and how to decompose into them, and how do we get benefit in terms of doing this kind of decomposition in removing the anomalies by reducing the redundancy in the design. In view of that, in the background of that, in this module we would try to understand a new kind of data dependency, an additional kind of data dependency, which is called multi-valued dependency, which can occur when an attribute can take multiple possible values, which we had eliminated in the first normal form together. And based on that, we will define fourth normal form and decomposition into 4NF, and then we will summarize this whole set of discussions of relational database design and talk little bit about what happens when you have temporal data in your system. So, these are the outline points based on our objectives, and we start with the discussion of multi-valued dependency. Consider a situation like this. So, here we are trying to represent an individual, a set of persons with 3 attributes: man, which is an maybe ID or name of that person, phones, and dog like. So, the idea is that here are persons and they can have 1, 2, 3 any number of phones, which is true for all of us, and then a person may have any number of dogs that he or she likes. So, both of these phones and dog like D, P and D attributes can take multiple values. And so, if we look at the 1NF normalized form here. So, in 1NF what we do? We create separate rows for them. So, we have created separate rows for M1 against P1 and P1 or P2 in phones, and similarly for D1 and D2. So, once we have done that, then we have here we can see I have highlighted with yellow, you can see the different redundancies that are arising, because since I have phones and dog liking attributes. So, it is possible that if phone takes 2 values and dog like takes 2 values, then actually 4 different combinations of them are possible, but in reality it may be actually these 2 are true, that M1 has phone P1 and likes dog D1, M1 has phone P2 and likes dog D2, but you could also have such redundant tuples coming in, because they are now valid. So, this is the situation which we try to capture in terms of what we say are multi-valued dependencies, which is shown in terms of double arrows, as you can see here. So, man I say determines multi-determines phones, man multi-determines dog like. So, there are 2 different multi-valued dependencies in this case. So, this multi-valued dependency adds a new source of redundancy in our data, and that is very real in various models of our system. So, let us move on. So, this is just another example. We have 2 different relations: student give the student ID and name, courses giving course ID and name, and the corresponding functional dependencies in them. You can see 2 instances of that. But if we as such there is no relationship between student and course, but if we choose to keep them in a single relation, say student course, which I have shown on bottom right here, then there will be, you can see lot of redundancies coming in, because since they can be in terms of all different combinations. So, S1 having name A may be taking course C1 having name C, but again the S1 having name A could be taking course C2 having name B. you just do not know which one is correct. So, you can see that here again you have two multi-valued dependencies, one where SID multi-determines CID and SID multi-determines CNAME. So, these are the two different multiple values that you can find against the SID, and this is so if two or more multi-valued dependencies exist in a relation, then while we convert we convert multi-valued attributes into single valued attributes, then the multi-valued dependency will show up. So, that is the basic problem that we would like to address. This is another example of two relations where the ID and child are together, where ID and phone number are together. So, naturally, if I combine them into a single relation, you have a set of possibilities of multiple different tuples, because given an ID there could be multiple children, there given an ID there could be multiple phone numbers. Mind you, this relation of inst info is still in Boyce code normal form, because there is no dependence, there is no functional dependency that holds on this relation. So, the key of this relation is the union of all the three attributes, and therefore, that being the key and no functional dependency holding on it, naturally vacuously makes it Boyce code normal form, but you can still see that there are redundancy in that data. So, now let us define multi-valued dependency in a formal way, and so we say that alpha multi-determines beta. Naturally, alpha and beta both have to be subsets of the given set of attributes. When do we say that? When there are for all pairs of tuples T1 and T2 such that they match on the fields of alpha. Till this point it looks like functional dependencies. There exist two more tuples T3 and T4 such that these conditions hold. What are the conditions? Look carefully. Here we say that all of them match on the alpha attributes, which is fine. Then we say that T3 matches with T1 in the beta attributes, and T3 matches on the remaining attributes with T2. Similarly, T4 matches with T2 in the beta attributes, and T4 matches with T1 on the remaining attributes. So, let us look at an example, gets confusing. So, here is course, book and lecturer. So, it is a relationship of university courses. Now, naturally, every course has multiple recommended books, and every course has been taken by multiple different lecturers from time to time. So, course can have multiple books. So, there is a multi-valued dependency here, it can be taught by multiple lecturers. So, there is a multi-valued dependency here, and therefore, I can have an instance of this particular relation, and I am just showing you how to test for the multi-valued dependency course multi-determines book. So, these are the four tuples I have marked T1, T2, T3, T4. If you look into the first condition, so this is your alpha, I am checking for, so this is alpha, this is beta, so this is beta, and this is so to say R minus beta minus alpha. Okay. So, the first condition that all these tuples will have to match on alpha, yes they do, all four of them have AHA here. So, that is fine. Take the second condition, T3 on beta is Silvers search and T1 on beta is also Silvers search. So, they match, and T3 on the remaining attributes are, if I take out beta, if I take out book, it is AHA, it is course and the lecturer that is remaining. Now, it already matches on the course. So, I do not have to check for that, but so I can just check for whether it matches on lecturer between. So, I am checking for this rule whether T3 and T2 match, yes T3 and T2 match, they have the same name for the lecturer. Look at the next one, which is T4 and T2 match on beta. T4 and T2 match on beta, yes they have the same name of the book, and whether T4 and T1 match on the lecturer, this rule, T4 and T1 match on the lecturer, this rule. So, it also satisfies. So, I can say that this relation has holds the multi-valued dependency course multi-determining book. In a similar way, you can mark your T1, T2, T3, T4 on this and check for course multi-determining the lecturer. Actually, we will soon state that if course multi-determines book, then it is trivial that course will also multi-determine lecturer. So, this is just to tell you, if you have 3 non-empty sets of attributes y, z and w, and then we say y multi-determines z if and only if there are these are the possible relations, that I can have y 1 and z 1 w 1 in a relation and y 1 and z 2 w 2 in the relation. Then I can have y 1 z 1 with w 2 and y 1 z 2 with w 1. That is, you can basically take the cross of these other 2 attributes, and those are tuples, possible tuples in your relation. And so, you can naturally, if you read it in a different way, then you can observe that since the behavior of z and w are identical, they are switchable. So, if y multi-determines z, then you have z y multi-determining w and vice versa. So, this is what is a core observation in terms of the multi-valued dependencies. So, this is in terms of our example. You can now clearly understand that ID multi-determines child name and ID multi-determines phone number in the earlier example that we took. And so, we can also note that if there is a functional dependency, y functionally determines z, then obviously y will multi-determine z. That is just quite obvious. So, we have to we can make use of multi-valued dependency to specify further constraints to remove redundancies and defining what is legal in a relation. And if a relation fails to satisfy a given multi-valued dependency, then we can construct a relation R primed that does satisfy the multi-valued dependency by adding tuples to that R. Right. Now, once having defined the notion of multi-valued dependency, we next proceed to check how do we reason about that. So, I would remind you about functional dependencies and the different rules of functional dependencies, the Armstrong's rules that we had introduced, all of these of augmentation, transitivity and all that. So, in terms of functional dependencies, we have 3 rules commonly called the CAT rules, which purely involve the functional dependencies. First is a complementation, which is a kind which we have just discussed, shown that if x multi-determines y, then x multi-determines R minus x union y, it multi-determines the remaining set of attributes. Augmentation, that is, I can augment any multi-valued dependency with left and putting attributes on the left and right hand side, as long as I put all attributes that I put on the right hand side, I put them on the left hand side. I may put more attributes on the left hand side, but all attributes that I put on the right hand side here z must be a subset of the attributes that I put on the left hand side. That augmentation is possible. Transitivity is manifesting in a little different way. If x multi-determines y and y multi-determines z, then x multi-determines z minus y. So, these are the 3 rules, which are basically these 3 are rules that involve only multi-valued dependencies, and the other 2 rules actually involve the relationship between multi-valued dependency, the replication rule and the coalescence rule, which are between the multi-valued dependency and the functional dependency. We are not going deeper into that further or trying to take specific examples and show how they work. I just want you to know that such rules exist through which you can define similar algorithms for multi-valued dependency also, as we did for functional dependency. Like, as you can understand, the most critical algorithm to define would be the algorithm of closure, which can again be used in the situation where I have functional as well as multi-valued dependency. So, just we will keep that in little bit advanced space of this course. So, just know that such things exist, but we are not going into the details of that. Finally, for a multi-valued dependency where x determines y, we call that MVD to be trivial if either y is a subset of x, which is the notion we used for functional dependencies, or there is a second condition here, that the union of the x and y, that left and right hand side, gives you the whole set of attributes. Otherwise, it is a non-trivial multivalued dependency, and we have to repeat the values. So, these are the two conditions. If they satisfy, then we know that we have a trivial multivalued dependency, and we do not want to deal with that. So, there is little bit of references to the theory given here. I have mentioned that there are closure algorithms. So, that given a set of dependencies, I will now generalize and say dependencies, which means that there could be functional dependencies as well as multivalued dependencies. Given a set of dependencies, you can define a closure of all of these functional and multivalued dependencies together that are implied by the given set, and we can have all those parallel definitions of closure of the dependencies, the minimal cover, canonical cover, and so on. So, I just want you to note that these things have been defined and they exist in theory, but will be beyond the current course that we are pursuing. So, it is now that we have seen another additional source of redundancy in our data in terms of multiple values and in terms of the multi-valued dependency that hold. So, we would now like to look into, if such dependencies exist, then how do you decompose a relation to satisfy that the redundancy caused by such dependencies are not affecting us. So, such a normal form, it is beyond the third normal form, is called to be said to be a fourth normal form, or 4NF, where you say that a relation is in 4NF if every multi-valued dependency alpha multidetermining beta in the closure of the set of dependencies is either trivial. Trivial means the left hand side is a subset of the right hand side, or the union of the left and right hand side gives you the whole set of attributes. So, it is either trivial, every dependency is either trivial, or alpha left hand side is a superset of the schema R. You can very well relate that this is just a little twist on the definition of the Boyce code normal form, where the second condition was identical, and the only thing in the first condition, instead of MVD you had a functional dependency. So, when we have this, we say we are a relation would be in the fourth normal form. Naturally, if a relation is in fourth normal form, it is trivial that it will be in the Boyce code normal form, but the reverse will not be necessarily true. So, again the same set of concepts, that if I have a set of dependencies and I have a decomposed relation, then a smaller relation, then I can project that set of dependencies in terms of a particular subset of the attributes, and here is the condition that is given. So, the decomposition algorithm into 4NF is exactly like the decomposition algorithm of the Boyce code normal form BCNF, only difference being that now you may be doing this crucial step of two-way decomposition for every multi-valued dependency also. Earlier we were doing this only for the functional dependency. So, now if there is any offending multi-valued dependency which is not satisfying the 4NF form, we can decompose the relation in terms of R1 and R2 as in here, which is exactly like the Boyce code normal form, and then the rest of it is simple. If it is by this another important point that you must note is, in this process you actually guarantee lossless join. So, this also continues to be in lossless join with every decomposition, and then you keep on repeating till all dependencies in F in your set has been dealt with the attributes in R1 and have converted them into the 4NF form. So, you have a total 4NF decomposition happening. Let us take a this here is the, like before, here is the formal algorithm for those who would be interested to formally study the steps. Here I am just showing examples of 4NF decomposition. So, we started this discussion with a person relational scheme having man, phone and dog likes MPD. I have added, I have just modified and I have added another attribute address. So, that in addition to the multi-valued dependencies, I can also have a functional dependency. So, we have two multi-valued dependencies like before, man multi-determining phones and man multi-determining dog like, but now I have a functional dependency man determining address. The key continues to be MPD. So, all of these dependencies will violate the 4NF, because none of them satisfy either of the condition that none of them are trivial, and for none of them left hand side is a super key, because the key is MPD. So, you can see that on instances of this relational schema, you will have multiple redundant records in the actual instance. So, on the right we normalize by taking FD1, take the union of man and phones, that gives you the first relation and then the rest of it. Then again you split based on FD2, you have the second relation in the decomposition man and dog like, and the third one gets generated as a byproduct of that, which is man and address. And you have three relations now, which together represents the original relation. Each one of them is in fourth normal form. Actually, what happens is when you have decomposed, then FD1 in this has become a relation where the multi-valued dependency man multi-determining phones can be checked in terms of a functional dependency itself, and that is what gives you the multi-valued dependency. And since it is multi-valued, so man and phones together continues to form the key. Similarly, in the second one, the man and dog like is the key, because you just have the multi-valued dependency, and given the same man you will have multiple dogs whom he or she likes. But in the third one, in the person address, where you have man and address, you have only man as the key, because man is a functional dependency that holds. So, this is a simple illustration of decomposition into 4NF. Here is a little more elaborate one. Again, this is we have I have worked through the steps. So, there are three multi-valued dependencies, and you can see that A multi-determining B is not does not hold the condition of 4NF. So, you have to decompose, you decompose, get R1 which is in 4NF and the remaining R2 which is also not in 4NF. So, you decompose in R3 which is in 4NF and R4, again R4 is not in 4NF. You decompose R4 into R5 and R6 and work through that, and you will be able to see that R5 is in 4NF and R6 also is in 4NF, which gives a complete multi-valued decomposition of this whole set. Naturally, with that we will conclude our discussion on the decomposition process. There would be some more aspects to look at, and there is lot of more normal forms that exist, but this is for all practical purposes. A database is normalized when it is represented in terms of the third normal form, and I have discussed the fourth normal form, because in some places people prefer to represent also in fourth normal form, so that they guarantee that they have even less redundancy in the data. But leaving that, let us quickly take a round in terms of what we have done so far and what is the basic overall design process that we should be following. So, again to remind you, the goal for our design is to have a relational database which is in BCNF or 3NF, has a lossless join due to the decomposition and dependency preservation. If we cannot achieve that, I am sorry, earlier what I meant is BCNF or 4NF, not BCNF and 3NF. So, the ideal would be I have a decomposition in BCNF and 4NF, lossless join and dependency preservation, which may not be achievable. If I cannot achieve that, then I have to sacrifice either the lack of dependency preservation. So, dependencies will have to be checked using natural join, or I will allow a little bit of redundancy and use the third normal form where I have the guarantee. Now, at this point you must wonder and note that SQL, the language in which we are doing the creation and the update and the query processing, that SQL does not provide any direct way of specifying or checking any dependency other than the functional dependency that checks the super key. Super key is the only functional dependency that SQL would check. No other functional dependency or multi-valued dependency or other type dependencies can be specified or checked in SQL. You can do that using assertions while discussing SQL. I had talked about assertions. We can do that using assertions, but that too is very expensive to test. So, it is not usually supported by any of the databases which are widely used, because that slows down your every process very much. So, you can understand that in terms of your design goals, you have to do a very good job to make sure that your functional and multi-valued dependencies are accurately expressed in the design, and accordingly the schemas are normalized in the proper ways, satisfying BCNF or 4NF or 3NF normal forms. But because while you will actually have instances, there will not be a practical way to see if you are violating any one or more of these rules of dependencies that you have set. So, as I mentioned, there are actually, these are not the only forms, there are various other normal forms as well, and fifth normal form, sixth normal form and so on, but it is very rarely, these are very rarely used. It is not easy to decompose into these normal forms, and by this decomposition does not give you enough returns in terms of the reduction of redundancy and removal of anomalies that people often would have motivation to do them, but you should know that such normal forms exist. So, in the overall process, if we look at what we have been doing is there are several tracks that we could be taking. One possible thing is the whole set of attributes have been generated while we have converted, or relation has been generated when you have converted the entity relationship diagram, the UML or the ER diagram, into a set of tables. That is how we got our set of attributes of the relational schema. It is also possible that we just started with a single relation containing all attributes, which is called the universal relation, and then normalization will break them into smaller relations. It could have been, or could have been, the result of some ad hoc design of relations also, and then we convert them. So, there are all different possible tracks that can happen. So, if we have taken the ER model track, then frankly speaking, if the ER model is carefully designed, then every entity defined in that ER model will have only the dependency which are the determining super key. So, just recall the employee, department, building kind of situation we discussed earlier. So, an employee entity has attributes department name and building, and there is a functional dependency from department name to building. So, what it means that in the entity relationship diagram itself, we did not do a good job. If we had done a good job, then we would have identified that the department itself is an entity, and therefore, would not feature as an attribute on the employee. So, it would have been, right there we would have, if we had called it as a separate entity, then that is equivalent of what we are doing now, taking the relation and then breaking it down through decomposition. So, functional dependencies from non-key attributes of a relation shape are possible, but are rare. So, mostly the relationships are binary, and if you do a careful design of the ER model, then many of these deep exercise of normalization you will not have to go through. It should also be kept in your view that there are times when you want to denormalize, want to use denormalized relations, because if you have normalized, then the only way to get back the original view is to perform join. So, if you have course, if you have prerequisites, and if you want to say view or print prerequisites with that title, title and course ID, naturally you will have to take a join with the course, which is expensive. So, one option could be, first alternative could be that you use a denormalized relation, where the course prerequisite is actually included in the course, and you know that will have violations of some of the normal forms, because there are functional dependencies between them. But that will certainly lead you to first a lookup, because you have them in the same table, you do not need to perform join, but you will need extra space, extra execution time for update, because you have redundant data, you have redundancy while programming on that, coding on that. Because of this redundancy, there could be possibility of error, because any of these anomalies can happen, and your code will have to now take care of that. So, it does help in certain way in terms of getting a better efficiency, but there is a cost to pay in a different way also. The other alternative could be, you can have a materialized view, which is actually the join on course of prerequisite. In terms of performance, it has the same benefit or the costs as you say, but only thing is you will not need to do that extra coding. So, it is better from that perspective. So, always keep the issue of denormalization in view, and do a careful design, that if it is very frequent that you will have to compute a join, then you might want to sacrifice some of the redundancy, some of the possibilities of having anomaly, and still have a denormalized design in your database. There are several other issues of design which do not get captured in what we have designed. For example, let us say very regularly we have returns, income tax returns to submit, and we maintain income tax return, tax, your sales tax return, and all that, and you maintain your accounts book of transactions, debit, credit, account head, and so on. Now, naturally these are all bound in terms of 1 year of activity. So, when the next year comes, then you need a separate set of records to be done for that year. So, how do you? So, if you have such a table where you, along with the company ID, you have year and amount, and then how do you take care of this situation? Because one way could be that you have all of these, you take out year from the attribute, and you have separate table in every year. So, you will have to create new table and remember their name. So, if queries which run across year will be difficult to do. The other way could be that you every new year you start renaming, you do a year where your earnings from different years are shown on different columns. So, you are basically every year you have the result in terms of a different attribute. So, that also is not a very good solution for a database. It is something which is with the spreadsheets will often use, but in terms of data which has a certain format and needs to be redefined from scratch at a different time frame in a different way, then you will come across these issues. Let me close with just pointing out that if we have one kind of data that we have not looked at, which are temporal in nature, that is, all that we have said is the attributes and their values. So, if we put a value to an attribute, then that value is taken to be the truth for now and for the past and for the future. So, if that value changes, then you completely erase that in the database. So, for example, today I stay at a certain address, tomorrow I may take up a different quarter, my address has changed. So, in our design, if there is against my employee ID there is an address given, then once I change my quarter, my address will change. It will not be possible to recollect what address I resided in say 2017. So, temporal data of such kind, temporal data of such kind have an association with an interval. So, a snapshot often does not solve the problem. So, you have to decide how you do that, whether you would like to put some attributes which specify the timestamp, or you would like to really have multi-valued attributes denoting the different time frames where they may have taken effect. There is no accepted standard, and the fact that if you know that it keeps on changing with time, then your original dependencies might get affected, they will change as well. So, these are the things that you will have to take care. This is another style that many a times when you have to say that okay, this course with this title existed from this semester, in a different semester the title may have changed. So, you can put a start and end attribute with that, which specifies what is the time for which the remaining attributes made sense. A good design, but these also have issues, because if you do this kind of temporal intervals, then how do you make sure that between two records the intervals are not overlapped. So, you are not saying that at the same time this course had name x, this course also had name y. So, they have to be disjoint. So, how do you check for this this consistency of data? There is no easy way to do that. So, the foreign key references and all those. So, handling of temporal data is another aspect which will have to be looked into very carefully in the design, and you will need to do some kind of design compromise, and implementation has to take care of those issues. So, to summarize, we have taken a full look into the multi-valued dependency and tried to understand what happens when your attributes get multiple values, learn the fourth normal form for that and the decomposition into that, and most importantly we have tried to summarize the core database design process that we have been discussing for the last 4 modules. This is the 5th one including this, and we have understood that, and we have talked a little bit about the temporal data, and with this we close our discussions on the relational database design, and from the next module we will move on to other aspects of the database systems.